Hi all, my name is ADEEB Sherif from Engineering Physics third year, and here I'm going to perform the linear variable differential transformers, also called as the Lvdt. So let me go through a little bit about the theory part, and then we can perform the experiment. Okay, right. So first of all, from the name itself, let's see what it is. It's a linearly variable. We are varying something linearly. Differential transform, and the output is differential form of something, and it looks like a transform. So a little more detail, we can say that this is a transducer. So what is a transducer actually? Transducer converts one type of energy into another. In this particular case, the rectilinear motion is converted into electrical signal. Rectilinear motion of what? Rectilinear motion of a core. As you can see in the picture of the right side, right bottom picture, there is a core which is moving right and left and all. So that motion we are calibrating to an electrical signal. That's what we are doing here. I'll go into the detail of that in the next slide. So here we have infinite resolution. That means like even if you move the tiniest, you can measure that in the electrical signal. So what's happening here actually? So here we have two coils, the primary coil and the secondary coils. So we are supplying an electrical signal, an AC signal in the primary coil, and there happens a mutual induction. So a mutual induction happens, and we are taking out the V out, the electrical EMF which is induced in the secondary coil outside, and we are calibrating it to the linear motion of the core. How can we calibrate it? As you can see in the shaded areas, in the shaded areas only the it's the affected zone of the electrical core. In that area only there will be a change in something due to the iron core, soft iron core. So that we can measure it. So by writing the physics of this, you can just concentrate on the red box. There is a non-linearity which appears. See, the thing is, we want a linear relation to what we are measuring and to what we are calibrating it into. So we are calibrating the linear motion into the electrical signal. Here the electrical signal is the Vd and the linear motion is the L. So we want a linear relation, but here we are getting a non-linear term also. So if we plot it, it comes a little bit linear than non-linear. Why little bit linear? Because if the L is very small, L is the length what we are measuring. I mean what we are displacement we are changing. So if L is small, the non-linear term vanishes off. So we can avoid the non-linearity in that kind of way. So if we plot the L versus V, there is a linear region for like about in the small region close to the origin, and then it's not linear. So if we stay in this particular region and perform the experiments, we can very well get the results and everything we want. So let's go to the experimental setup then. Here we have the linear variable transformer, the setup. Here in the top picture, that from that box we'll read the modulated output. Modulated output means the direct output which is coming out from it. Uh, I'm sorry, the demodulated one. The demodulated one will measure in this digital one, and the modulated one we are measuring in the oscilloscope. Why? The modulated one, it varies, it's an AC, so we can't measure it directly in the digital display. And here are the graphs which I talked about and the diagrammatic representation of the setup. So demodulation I told because like why we are doing demodulation actually here. So because we want to take the reading in a digital form, we can't take an AC signals reading in that way. So we will modulate it with a carrier wave such that we will be able to read it in the digital display. That's why we are demodulating it. So you give a carrier of the same frequency or something, then pass a low pass filter so that high frequency will be cut off, and we get the demodulated signal, which is an DC signal. So we can display it in a digital display. So in the experiment, what are we doing? Only three things we are taking the readings of. We move the core. So we take the displacement of the core, and we note down the modulated output which is from the oscilloscope, and the demodulated output which we take from the digital display, the red color display, which I will show you in a minute now. So here's the experimental setup. This is the iron core and the setups and all. Here we will move this iron core left and right using the mouse kind of scroll is there. We move it up and down, and we'll do that. I will show you in a minute. So this is that setup, and this is the demodulated output, which is a digital display we are seeing. And here we have the modulated output, which is shown in an oscilloscope. So which readings we take? In the right side you can see so many things, Vmax, Vrms, frequency, duty cycle, rise time and all. We take the Vrms. So in this particular oscilloscope, actually we connected to channel 1, which is the yellow color shown here. The second one is not important for us, only the yellow color thing we are concerned about. So we take the RMS value, the first one value of the yellow color wave, as the modulated output. Okay, so that's what. Now let's see, I told you, there's a mouse kind of scroll in it. If we move it up and down, the modulator and demodulator will change. I'll show it to you. So I'm changing the, I see there is a change in the demodulated one as well as in the modulated one also. If you focus on the VRMS, it's 3.96 now, 3.99, 4.02, 4.06, 4.07, 4.09. So that's the reading we are taking here. So let me try and show you an example. As you can see, there is one golden color line here. Let me focus. Yeah, I'm sorry. Yeah, there is one golden color line here. You can see here there is one golden color line. We are making it into -6. I want to measure when the iron core is at -6, what is the modulated and what is the demodulated. Okay. Yeah, this is almost -6. Golden color is almost to -6 now. Now let's see the demodulated one. Demodulated is 58.5, and modulated VRMS it is 4.06, 4.05 around there. And we'll write these readings down. So I'll show you the observation table in the next page. So this is the results we are getting. I told you there are three things we are measuring. Just these three things: displacement, modulated, demodulated. Displacement we can measure from that scale itself. Modulated we are measuring from the oscilloscope VRMS. Demodulated we are measuring it from the that a digital display. So after writing all this down, we'll do it for -6, -5.5, -5, and we'll go till +6 centimeters. And then we have two graphs. We have to plot displacement versus output for modulated one also, demodulated one also. So after plotting it, you will get something similar to this. The main difference is demodulated can contain the negative values. And the significance of the negative values is, if it is negative, if the displacement is negative, that means the core is in the other side, and if it is positive, it is in the other side. If it is right side, then left side. This side we can differentiate, but in modulated output we can't know in which direction it is. Is it in the left, or is it is in the right? So as you can see in this picture, the core can go towards up, towards the left color, left one, and it can go to the right side also. That we can't differentiate in the modulated one, but we can do it in the demodulated one, because it is obvious. In the modulated one we are taking the VRMS. So VRMS is the root mean square velocity. So we are squaring it, taking square root. So there will be no negative. So that sign will be lost in modulated, but we can get back in demodulated. So yeah, that's the main inferences we can make it from here. So we are directly changing the linear motion into an electrical signal, and we saw that it's linear in a particular range only, and it has infinite resolution. Even if you move a little bit the iron core, you can take out the electrical signal from that. And the sign change, as I told, like we can know the sign change in the demodulated. So here are the sources which I used. So yeah, thank you for your attention. Thank you.